Hey there. Did you know there's a secret language you're already speaking every single day? You probably don't even realize it. It's the language of how we organize, well, everything. It's all about groups, and it's one of the most powerful ideas out there. So let's get right into it.
I mean, just think about your own life for a second. Your friends, right? You've got your game night crew, your hiking buddies, or what about your groceries? You split them up. Produce, dairy, snacks. Your music playlists, workout jams, chill focus. See? You're constantly creating these little groups, these collections, these categories.
Well, that simple thing you do, that totally intuitive act of just grouping stuff together, guess what? That's the core of a huge mathematical idea called a set. Yep, turns out you've been a set theorist all along, and you didn't even know it.
So let's make it official. Here's what we're going to cover. First, the basic language for groups. Then, how to actually describe a set. We'll meet the whole set family tree, see what happens when they interact, and then wrap up with the really cool big picture stuff.
All right, first things first. We've got to learn the fundamental rules. Just like any language, this one has grammar, and we're going to start with the most important word of all.
Okay, so what is a set, really? Put simply, it's a collection of well-defined objects. Now, the word collection, that's pretty straightforward, but that other part, well-defined, that's the key. It's the magic ingredient that turns a random list into a proper mathematical set.
So check this out. If I say the collection of tall students in a class, that's not great. It's not well-defined. Why? Because what I think is tall might be totally different from what you think is tall. It's vague. But if I say the collection of students with heights between 135 and 160 centimeters, boom, that's crystal clear. For any given student, you can say with 100% certainty, yes, you're in or no, you're out. There's zero confusion. And that precision, that's exactly why things like computer databases are built on this very idea.
Okay, so here's the basic grammar you need to know. It's super simple. We name sets with capital letters, like A or B. The things inside the set, we call those elements, and you'll always see them wrapped in these squiggly curly braces. And then you have these two symbols. They're kind of like the verbs. The E symbol means is an element of or belongs to. And the one with the line through it, you guessed it, does not belong to. It's a really simple, clean system.
Okay, so we've got the grammar down. Now let's actually write something. Turns out there are two main ways to describe a set. You can think of it like giving someone directions. You could list out every single turn, or you could just point them toward a landmark.
Let's stick with a really simple example to see how both ways work. We'll use the set of all the vowels in the English alphabet, and we'll just call it set V for short.
All right, method one is called the roster form. It's just a fancy way of saying make a list. Seriously, that's all it is. You just list out every single member of the set. So for our vowels, set V would look like this: A, E, I, O, U. Simple, right? It's like taking attendance.
Okay, method 2 is the set builder form. This one's a little different. Instead of listing everything out, you just write the rule that everyone in the group has to follow. For our vowel set, it would look a bit like code. The way you read that out loud is, V is the set of all things, let's call them X, such that X is a vowel in the English alphabet. So you see, it's the rule, not the roster.
Awesome. Now that we know how to write sets, let's meet some of the different types. You can think of them as different characters in the set universe, each with its own little quirk. First up, you have your finite set. That just means you can count the elements, and there's an end. Its opposite, of course, is the infinite set, which, goes on forever, like all the numbers. Then there's the singleton set, kind of lonely, it only has one single element. And last but not least, the super important empty set. It has 0 elements, nothing, nada. And we use this cool circle with a line through it to represent.
Okay, let's tackle something that trips a lot of people up: the difference between equivalent sets and equal sets. It's pretty simple, actually. Equivalent just means they have the same number of things in them. The things themselves could be totally different. But equal sets, they have to have the exact same members. The order you list them in doesn't matter, but the elements have to be identical. So think of it this way. All equal sets are also equivalent, but it doesn't work the other way around.
Okay, so we've met all the players. Now for the fun part. This is the action. What happens when these sets start interacting with each other? We call these operations. And honestly, this is the magic behind how search engines work, how databases can sift through mountains of data to find just one thing.
First up is the union. You'll see this U symbol. Just think of it as a merger or a team up. You're just taking two sets and smooshing them together into one big set that has everything from both.
And one little rule, if something is in both original sets, like the number 6 in this example, you only write it down once in the new set. No duplicates.
Next, we have the intersection. It's that upside-down U symbol. And this one is all about finding what's in common, the overlap. The new set only gets the elements that are in both set A and set B. So, looking at our example, the only thing they share is the number 6. That's the intersection.
And finally, there's the difference. This is basically just subtraction. When you see A minus B, it means you start with everything in set A, and then you take away anything that's also in set B. You're just removing the common stuff, leaving only what's unique to A.
Okay, for our last part, let's zoom out a bit and talk about relationships and scale. This is where things get really, really interesting. We're going to see how sets can fit inside of other sets and the mind-blowing math that goes along with it.
So what's a subset? It's pretty intuitive. A set is a subset of another one if all of its members are also inside that bigger set. Every single one. That's the key. If you can find every element from set P also inside set Q, then P is a subset of Q. It's like having a small box of tools, and every single one of those tools is also in your giant toolbox.
And here's where my mind gets a little blown. If you want to figure out exactly how many different subsets you can possibly make from a set, there's this elegant, simple formula. 2 to the power of n. That's it. And n is just the number of elements you started with. Just look at how this plays out. If you have a set with nothing in it, the empty set, you can still make one subset, the empty set itself. Okay, now a set with just one element, you can make 2 subsets. Add another element, so now you have 2. Boom, you can make 4 subsets. Add a third, you leap to 8. It's not adding, it's multiplying. It's exponential growth.
I mean, just let that sink in. That's the big idea right here. Every time you add just one more thing to a set, you literally double the number of possible smaller groups you can make from it. The complexity, the number of combinations, it just explodes. It's kind of amazing.
So there you have it. We've basically just put a formal language to something you do all the time without even thinking about it. And this simple idea, it's the bedrock of computer programming, databases, and so much of logical thinking. So I'll leave you with this question. Now that you know the language, where are you going to start seeing it?